So previously we mentioned that any vector can be broken down into two components. Here we have a vector u. We're breaking down it into its two components. Its horizontal component w1 and its vertical component w2. You see that w1 is orthogonal or perpendicular to a second vector v. We can also see that w1 is parallel to vector v, or w1 is a scalar multiple of vector v. And here we can see that w1 is actually about 1/2 of what vector v is. So we're saying that u is equal to w2 plus w1. And if we're to actually, connect this side over here and do our terminal side to the initial side and continue up with w2, we can see that w1 plus w2 is actually equal to u. So u is equal to w1 plus w2. Now we define w1 as a projection of u onto our second vector v. So, and we write this as w1 is equal to the projection of u onto v. Now to calculate the actual value of this projection onto vector v, we say that w1 is equal to the dot product of u times v divided by the magnitude of v squared. Now this will give us a scalar quantity, and then we're going to multiply this scalar quantity by the vector v. So our result answer for our projection is going to be a vector quantity. So to find this projection, once again, it's a dot product of the two vectors divided by the magnitude of v squared times the vector itself, v. Now to find w2, we know that w1 plus w2 is equal to u. So if we subtract w1 from u, that will give us w2. So here in this example, we're being asked to find the projection of vector u onto vector v. Then write u as the sum of the two orthogonal vectors, which is our w1 and w2, the components of u, one of which is the projection of u onto v. We know to find the projection of u onto v, that's our w1, which is equal to the dot product of u times v all over the magnitude of v squared times the vector v itself. So to find the dot product of u times v, this is -3 times -4, which is a +12, plus -2 times -1, which is 2. So this becomes 14. And the magnitude of v would be -4 squared, which is 16, plus -1, which is 17, 1. So 16 plus 1 is 17. So the magnitude of v would be the square root of 17. Now when we square the square root of 17, that just gives us 17. So this reduces to just 14 over 17 times vector v, which is -4, -1. And if we distribute our 14 over 17 times this, we get -56, 17 and -14, 17. Now the reason why we distribute this over this to get this is so that now we can subtract w1 from w2, from u1, because we know w2 is equal to u minus w1. So this is our u, which is -3, -2, and we're going to subtract the w1 that we just found so we can get w2. So this minus this will give us 517 minus 20, 17. So it's -3 minus 56 over 17, which gives us a positive 517, and -2 minus 14 over 17, which gives us a -2017. Now here we can factor out the 517s, which gives us 1 and -4. So this is equal to w2, and here 14 over 17 times -4, -1, it would be equal to w1. So those are the two components of vector u. Now, to write u as a sum of the two vectors, we can rewrite this as u is equal to 14 over 17, -4, negative 1 plus 5 over 17 times 1 and negative 4. And once we do the calculations, we'll see that these two vectors will give us back negative 3, negative 2. So our next section here deals with finding work. Work is calculated as the force in the direction that an object is moving times the total distance moved. So here we have a force pulling on this object in this direction, and the object is actually moving along the plane, the path here from P to Q. So the distance is actually from P to Q. So, but even though our force is F, we're only interested in the projection of F onto PQ, or the horizontal component, since work is the force in the direction the object is moving. So, a work then is equal to the projection of F onto PQ, which is a horizontal component, times the distance P to Q, which is written as the magnitude of PQ. To find the projection of F onto PQ, we can do F cosine theta. Since we know cosine theta is adjacent over hypotenuse, then F cosine theta will give us our adjacent side, which is the equivalent of the projection of F onto PQ. So now we have the projection here times the distance, we can actually find the work done. Now we're going to look at an example that demonstrates this. In this example, we're told that a force of 45 pounds exerted at an angle of 30 degrees on a table to slide it 20 feet across the floor. So we're trying to determine how much work is done in sliding this table 20 feet across the floor. From our formula, we know that work is equal to F cosine theta times the distance moved. So we have our force, we have theta, and we have the distance moved. So this is simply just the force, which is 45 pounds, times the cosine of 30, times the distance moved, which is 20 feet. So this comes out to be approximately 779.4 foot-pound.